Everything is fine? No question? Everything is fine? This is not you. This is what we have done in previous class. Okay. If you have no question, let's check the exit ticket. If I have any comment here, let's check this one. If I have any question, this is week number 7. No question here, huh? I have no question here on week number 7. Okay. What was the last thing that we stopped? Do you remember? If I want to recap quickly. So if we want to recap what we have learned, so we just start to call something to be relation, and the what was the definition of relation always is given in the problem. There are several examples, like you can say x is related to the y by x to be less than equals y. You can say x is related to the y by x to be this to have the same remainder in like mod 3, or you can say x related to the y by give me one more. So like just say x is divisible by y. Just different types of relations that we have had in last class. And then the relations could be reflexive, and like reflexive means for whichever x that you choose, x is related to the x. It could be symmetric, and that means for whichever x and y we choose, if x is related to the y, then y also related to the x, so that would be symmetric. It could be anti-symmetric. If you're for whichever x and y in the relation x is related to the y and y is related to the x, so there is no way unless x and y to be the same. That's anti-symmetric. And then we have transitive. Transitive means for whichever x, y, z that we choose, if you have x related to the y and y is related to the z, then x is related to the z. We have had two types of relation. It could be partial order relation, which with the set is called PO, partial PO set. So PO set means partial order relation. If you have a reflexive property, if you have anti-symmetric property, and if you have transitive property. So this is called partial order. And then we have the other one, which is equivalency relation. Equivalency relation is a reflexive and symmetric and transitive relation. And then we had another terminology of totally ordered relation. If it is already posted, so means it does have all reflexive, anti-symmetric and transitive plus comparable, which is for whichever x and y, either x is related to the y or y is related to the x. So that's a totally ordered set. We can just write the examples. Oh, sorry. Always get rid of Thank you. Okay, is this fine? What else did we learn? What else did we learn? What else did we learn in the previous class? You can just bring the examples, right? So like partially ordered example could be that inequality. It's one example. Divisibility was another example. For equivalency, that, what was it, mod was one example. Equality is another example. So actually for totally ordered also we have inequalities, totally ordered relation. So this is what we have done in previous class, right? So the last thing we stopped was just class of equivalency. We were trying to make the class of equivalency. We were trying to make the class of equivalency. Can I move on? Okay. This part stopped on class of equivalency. So we just did only one class of equivalency, which was for even number and odd numbers. So I have to define what's a class of equivalency as a recap and then just start to do some examples. So this is the first place that we've seen the class of equivalency. This is the first place that we've seen the class of equivalency. It says the class of equivalency is defined. The class of equivalency is defined the set of all members, that's related to the one element, okay? So class of equivalency basically make the partitions. So it will make a partitions. Like if for the previous example, I can recap. So that was my class of equivalency for the relation x to be related to the y by this definition, means x and y has the same remainder when you divide it by 2. So your remainder when you divide it by 2 either could be 0 or it could be 1. So it could be 0 or 1 because that's the only possibilities when you're dividing by 2. So which the remainder of 0 gives you even numbers, the remainder of 1 gives you your odd numbers, right? So the thing is, if you do such a this thing, your set of all integers, if you have the set of all integers, is dividing exactly to two different parts, two different partitions. One is all elements, which is in class of 0, means it has the same remainder as 0, 2, 4. And the other one is one, what was it? The set of all elements that has the remainder of 1, huh? So do you have any intersection between these two classes of equivalency?
There is no intersection.
What happens if you union these two?
It's all.
The set of all integers. So these two properties, number 1 and number 2, is called what we have partitions. So when you have partitions of integers, you're having no intersections. And if you put them integers, if you have no intersection, if you put them together, you make the whole set. So we can try one more time. So let's say if your relation as an example, I'm pretty sure we have the example somewhere, but I just want to do it right now because I've done just this definition here. So let's say your relation was defined like just x to be equivalent to the y in mod maybe 6, okay? So then you're having class of equivalency for everything which has the same remainder as 0, everything that has the same remainder as 1, everything that has the same remainder of 2, and then 3, and then 4, and then 5, right? So those are all your possible class of equivalency. So what was definition of being in the same class is the set of all elements in the integers that has the same remainder as 0 when you dividing by 6, which we know what they are, right? 6, 12, 18, so on. 1 is the set of all integers which has the same remainder as 1 in mod 6, which again we know what they are, 7, 13, and 19, and so on. And so on. You can just make all of these class of equivalency in mod 6. So this is for 2, and this is for 3. So the all elements which has the same remainder as 3 when you're dividing by 6, and the all integers which has the same remainder of the 4 when you're dividing by 6, and then all elements which has the same remainder as 5 when you're dividing by 6. Do I have any other possible class of equivalency? So this is 17, this is 23, and so on. I've added only 1 to the previous step, right?
Is 1 not included in the second row?
Yes, it is, because it is integers.
So the increase in 0.
I have to add 1 element on this side, okay? Sorry, I'm erasing. I have had, thank you, 1, 7. I have had 2 and 8. I have had 3. And I have had 4. And I have had 5. Okay. So what's happening? You're having a set of all integers, which is dividing by 1, 2, 3, 4, 5, and 6. The one which has the same remainder as 0, the one which has the same remainder as 1, the one which has the same remainder as 2, 3 when you're dividing by 6, 4 when you're dividing by 6, and 5 dividing by 6, okay? So the set of all integers is divided by 6 different class of equivalency which has no intersection. So there is no way these 2 class of equivalency have the same element. There is no way any of these 2 class of equivalency have the same element. And if you put all of these numbers, all of these class of equivalency 2, and then 3, and then 4, and then 5 union, okay? So that notation is union. It makes the whole entire integers. That's what we call partitions. This is called partitions. For partitions, we need to have no intersection. We need to have the whole entire class of equivalency, make the whichever domain you have. Here is integers. Okay. This is still a recap from last class. Okay, so I've done the class of equivalency. I've done one more example to add the concept of partitions. Any question here? Do you have any question here? Any comment? No? Anything to add here? So we have some more examples here in different way. So this is my another example for class of equivalency. This says the relation is given to me. So that's just given by ordered pairs. This is the relation that is directly given by ordered pairs. So means one is related to the one. So, you know, when you have a one and one in the relation, that means one is related to the one. And I don't know what's the relation, okay? I could know, but that's fine. So when you have 1 and 3 in the relation, so that means exactly the first element is related to the second element. That's how we write it, okay? So according to this relation, whichever is given to us, your inputs are the x, so means it's just really x is the set of x is your inputs and the set of x is your output. So your relation is defined from same set to the same set. It says it's a class of, it says it's equivalency relation. It says it's equivalency relation, so we can check. So means it's reflexive, it's transitive, and it's symmetric, okay? So that's what it says. So then we try to write the class of equivalency for whichever numbers, which is what is related to the one, and then whichever number is related to the two, whichever number is related to the 3, 4, 5, and 6, okay? So we can just rewrite whichever number is related to the one. So your definition one more time over here is going to be the class of A, set of all x's, which x is related to the A, okay? So that means your elements with the second component of the one is what you're looking for. No more, right? That's just only. So then your, what was it? Class of one has 1, 3, and 5. Class of one has 1, 3, and 5. Is that okay? So your second element has to be 1, okay? One more time. If you're supposed to write the class of 2, sorry, right over here, I have class of 3. So class of 3. So if I'm writing class of 3, I'm going to clean up all things. So class of 3, class of 3 is the set of all x's, which x is related to the 3. That means here, 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 and that's it, right? So you have 1, 3, and 5. Class of 3 is 1, 3, and 5. Class of 4 is the set of all x's, which x is first element and 4 is your second element. I have, where is it? Only here, right? No more 4. It has only 4. And then same thing for the 5, same thing for the 6, right? So I'm just writing definition. That's just really key part. The second element or the right side has to be 5. And whichever number is, what was it for the 5? Was here, and was here. So 1, 3, and 5.
I have a question.
Mm-hmm.
It's more about notation than anything. The equivalence class red bracket 1, is the bracket notation always that rule, or can you change that rule to whatever you want? Like, will there be another example where it says consists of all x such that x is 1 times whatever? Like, is that notation?
The bracket notation,
Yeah,
the
yeah.
bracket notation always is just showing the class of that one. So
Okay,
they
and that's the class?
yeah. So this, you're talking about this square bracket notation, right?
Mhm.
So that's always showing the class of equivalency. There is no other notation for that.
Okay. got it.
Okay, but then we have to just have the other bracket notation, which is just when you're showing ordered pairs. So it's just parentheses. The right side has to be what you're looking for. And then you're basically showing as a set, right? So you're basically showing as a set of elements. So this class of the 3 is set of all elements that is related to the 3. Okay, So it's a set of elements from the whichever domain you choose that's related to the tree. Okay. So this is not partitions, right? So that's why I brought the partition first. So this is not partitions because we have several things that even they are equal, like class of three, which was 135, and class of 5, which is also 135. So class of 3 and 5 are the same. Class of 2 and 6 are the same. So this is not what we are looking for as partitions, right? So partitions has no intersection, but we have some classes which are exactly the same here, okay? So these are not making partitions. Can I make a partitions now by this example? If that's the goal? Like what? You can have class of 1, class of 1,
and then delete class of 3 and 5. So we're
class of 2, class of 3. Is there any intersection between class of 3 and 2?
No.
Any intersection between class of 1 and 2? No. No, right? Any intersection between class of 1 and 3?
Yes.
They are the same. So looks like this, 1 and 2.
And then 4 2 4. Because 4
4 is by itself. Do you see how we are doing? Do you see how we are doing? We don't want to get any intersection. If we have a repeated terms, we just make them, one of them to be there, right? So, but if it was, that's just really good example because it doesn't have any repetition between any of these elements. So either they are exactly the same or they are completely different. So that's why we could make the partitions. So according to what we have in this example, class of 1 is the same as class of 3 and is the same as class of 5. And class of 2 is the same as class of 6. So class of 4 is different. 1, 2, 3, 4, 5. Yeah. So we have all of them. Okay. And that makes sense because in our maybe even odd numbers, that's what's exactly happening, right? So class of 0 is the same as class of 2, is the same as class of 4, right? And then for any of those numbers, right, class of 1 is the same as class of 3, and same for the rest of odd numbers, right? So that makes sense. So there are classes that they are exactly the same. Depends on what's the relation, okay?
Would you call this restricting the domain?
Restrict.
Or is it something else?
Which one?
What we just did with excluding 3, 5, and the other one 6.
We didn't exclude, they were the same. We didn't exclude anything.
No,
It
no,
was really the same.
I'm saying if we wanted to make a partition and I said, okay, let's exclude this, would that be called restricting the domain or, okay.
No, because we have entire elements. Of 1, 2, 3, 4, 5 covered by all of this, right? So is that true or not? So if you put if I want to just complete my partitions, the rest of thing that you need to make sure, if you put the 1 union 3, union, which one is it? 2, union 4, you have to have the whole entire X. Do you? 1, 3, 5 was for 1. 2 was for the 2 and 6, and then 4. You see, it does cover the entire. Okay. So we did not restrict our access. It still is the same. Here we are. So that's exactly what we were discussing. The classes of 1, 3, 5 are the same. 2 and 4 are the same for this equivalency relation. And then it has another example. It says your relation is given by only these 3 elements, which is only reflexive. A is related A, B is related B, C is related to C. So the claim is this is also symmetric. This is also transitive. Agree with that? AA symmetric AA, BB symmetric BB, CC symmetric CC. Transitive, what the transitive says, Transitive, if A is related to the B, B related to the C, A and C must be related, but you don't have the rest, right? So you have only AA. You don't have any other element that to be, you see, like you just true, false, right? When you say A is related to the B and B is related to the C, transitive says A has to be related to the C. When your equation or whichever relation you have over here has none of those, so then it doesn't matter what's the next, it could be whichever, right? So when your first one is false, so then the statement is going to be always true. So because your statement doesn't have anything except A, B, B, C, C, okay?
Would you call that redundant? Because you say transitive, and I think to myself, but would you call that redundant, or do you think it's important to explicitly say that it is transitive?
Because it's class of equivalence. Because I'm looking for class of equivalency, it's important to be
Okay.
transitive.
Okay, I understand.
If it's not equivalence relation, so how I'm going to talk about class of equivalency? Okay, so that's why it's important to make sure it's reflexive, it's just symmetric and transitive. So then it's equivalency relation. So then I can talk about the class. Okay. So for this one, your class of equivalency for A has only A. Class of equivalency for B has only B. The class of equivalency for C has only C. Okay, which is okay. Is it partition? Is this partition? Do I have any intersection? No. If I union them, do I make the whole entire set? Yes. So that's partition. Okay. This is another example. This time your set is numbers from 1 to 10. Your relation is defined, the 3 divides x minus y. 3 divides x minus y. Does it make sense? What's the relation exactly? Let me rewrite it. So what does it mean if you're having x related to the y, and this is the same or is defined to be 3 divides x minus y? This is the same as saying x minus y equals 3 times k for some k.
Like 4 and 1.
I'm looking for you guys. So just give me one example. I'm looking for you giving me one example. Or you can think about, do I know anything else about this relation? I've seen this relation before. If the difference of the numbers has divisible by 3, it's mod. So this is the same as what? X and y has the same remainder in mod 3. Isn't it interesting? Is that's really the same relation, but it's different way of saying. It is really the same relation, different way. So when you see the 3 divides by x minus y, basically means x equivalent to y, or it has the same remainder with the y in mod 3. Do you agree with this one? Based on the mod definition?
Okay, yes. 4. Yeah, 4 1. Okay. And then it just continues up to 10.
Is this okay? Can you follow why this is the same relation as mod in 3? Based on what I wrote over here? No, why? No. Anyone has? They're thinking about. The difference is multiple of 3, exactly.
Except it starts at 1 rather than 0.
Start at 1, yeah. So my main question I'm waiting for you guys to really adjust what's this as given definition of my relation, which was this as what we figure out to be the same. Do you agree with this one? Yes. So one more time, if I'm looking with the numbers, let's just look at with the numbers. So according to what's over here, it says 3 divides x minus y. So you're looking for class of 1. You have to look for numbers which 3 divides x minus 1. 3 divides x minus 1. So you're looking for all of the numbers x which has the same remainder as 1 in mod 3, according to what we got on top. So 3 divides x minus 1 is the same as which numbers from 1 to 10 has the same remainder as 1 in mod 3. That's exactly second way of definition, what we call mod. Okay. Similarly over here, when you have class of 2, you're looking for all numbers from 1 to 10, which has the same remainder of 2 when you divide by 3. And you're looking for all numbers which has the same remainder of 3 when you are dividing by 3 over here, which is the same as 0. Okay. So for the same reason, we go ahead.
Can you explain how the 1 and 2 are included?
1 and 2 are
So
included.
1 and if you say 1, 4, 7, 10, why is the 1 included?
So let's say if you divide 1 by 3, it's nothing. And you're subtracting and your remainder is still 1. That makes sense, right? So the same thing for 2. When you divide it by 3 and it's nothing, so you're subtracting, so your remainder is 2. So that's part of your sets which has the same remainder as 1. That has the same remainder of 2 for 2, okay?
Can I tell you how I approach this and then see if it makes sense to you? So this is just the first thing that I did. I would define x related to y to mean that 3 divides x minus y. So I said, okay, I want x minus y to be divisible by 3. And I said, okay, 4 and 1. If 4 is x and y is 1, then 4 minus 1 is 3, and 3 is divisible by 3. So I include those two numbers. And then you can go up to the end of that set x in the domain. And then you just pick the next number that can include those two. So 7 minus 1 is 6, and that's divisible by 3. 7 minus 4 is 3, and that's divisible by 3. And then you just repeat that until you get the end. So does that make sense?
That makes sense, yeah.
Okay.
That's exactly that's what I'm trying really to tell you. So I'm trying to say this fact that the subtraction is divisible by 3 is the same as this fact that we've seen it in previous chapters. Okay, it's different exactly ways or equivalent definition for the same mod that we've seen before. Okay, so whichever makes more sense for you, you can use either one. Okay, so the mod that we've seen in previous chapter equivalents to the difference of numbers is divisible by the same number of whichever modulus you have. Okay, and then that's just similar to any other process that we have done. The remainder of 1 and 4 and 7 and 10 are the same, right? So if you choose any of those elements, the class of equivalency will be the same. If you choose any 2, 5, and 8, they should have the same remainder when you're dividing by 3. So that's why they have the same class of equivalency. So if you choose 3, 6, and 9, they have the same class of equivalency. And that makes sense. Okay. Do you have question? Sure. Any question? Okay. So I have to say what is the relation between the class of equivalency right over here. So if you're having a relation, which is already reflexive, symmetric, and anti-symmetric, symmetric and transitive, and it's a finite set. If it's on the finite set, so then each of the class of equivalency has exactly R elements. Each of the class of equivalency has exactly all R elements. So then how many class of equivalency do I have? So it's the total number of elements I have divided by R. That makes sense, right? So if your class of equivalency has 2 elements, and then your total has 10 elements, 10 divided by 2, so then you have to have 5 class of equivalency.
That is the cardinality notation, right?
The top is cardinality notation.
So the not absolute value of cardinality. with
So
the X?
the cardinality of X for the previous example.
Okay,
What is the cardinality of X for this example?
it's 1 through 10.
Which
So,
is 10?
yeah.
And then each class of equivalency has how many elements? How many elements I have in, actually they are not equal.
Yeah, it's 4.
So you can't say this
It's
one.
not perfect.
No, this is not perfect. Yeah, I was just dividing to say how many class of equivalency we have. Later we have pigeonholes principle, so we can just say about this one, but not now, right? So if there was any of this class of equivalency, maybe exactly 3 elements. So then you have 10 divided by 3 elements, which you can round it 3.3. So that would be 4 class of equivalency. So you expect to get 4 class of equivalency, okay? But we can't talk it right now because we don't know the pigeonholes. We will learn, okay? The reason that I couldn't complete with this example was this has 4 elements, this has 3. Here it says all of them to be R. Okay? But obviously we can talk about the class of equivalency in mod 2. Class of equivalency in mod 2, we have exactly 2 class of equivalency. I explained in previous class. The class of equivalency for 0 gives you all even numbers. Class of equivalency for 1, it gives you all odd numbers. And then the possible even numbers and odd numbers is the total number of class of equivalency we have. Okay. And then I said, what's the partitions, right? Partitions means you should have no intersection, which makes sense. Even and odd has no intersection. And the union of them must make the whole entire Z, which is the class of equivalency. Okay. We tried it for mod, what was it? 2. We tried it for mod 6 in this class, just at the beginning for recap. So here it says, can you try the same process that you have done for mod M? Okay, so this example tried to just extend our concept of mod and the partitions. Consider you have any arbitrary elements of the M, which is greater than equals 2. It's nothing just really special, it's something bigger than 2. And then your definition says X is related to the Y in mod M, okay? And then it's the same as M divides Y minus X. So this is just the same thing that we practice on mod 3 on top. Prove that the class of, what was it? First of all, this is equivalency relation. That's number 1. And then what would be the class of equivalency for this one and how many of them do I have? Based on what we tried for mod 2 and mod 6, can you tell me how many class of equivalency you have before starting the process?
N minus 1. Oh, no.
Including 0. So
So
0, 1, 2, 3 to the M minus 1. So it's going to be M, huh?
yeah.
Plus 0 is M.
So
Okay.
yeah, for mod 2, it's 2 sets.
So for mod 2 is class of 0, class of 1. So it's 2 of them. Mod 3 is class of 0, class of 1, class of 2. So it's 3 of them. Okay. So for mod M is M of them. Okay. So let's just answer the first part of the question. The first part of question says, prove this is equivalency relation. So to prove something is equivalency, relation, First, it has to be reflexive. What is the reflexive? Reflexive means X has the same remainder as X in mod M. And according to this way of definition, X minus X must have X minus X must have some number times M for some K, which is 0 works, which 0 works. So does X and X the same has the same remainder? Yes, because they are the same. Or you can say K equals 0. So this is reflexive. Number 2, symmetric. Symmetric says if X and Y has the same remainder in mod M, you need to show Y and X also has the same remainder. So this is so obvious, huh? Because if your M divides X, Y minus X, if your M divides Y minus X, or you can just say Y minus X equals K times of M for some K. So then you can multiply by a negative both sides. So then X minus Y is negative K times M for some K. Do you agree? This is the same as saying M divides X minus Y. This is the same as saying this time Y and X has the mod X. Sorry, mod M. I don't know why I wrote mod X. Mod M. I'm sorry. Do I need to write all of these lines in orange to just show X and Y are the same remainders, or Y and X are the same remainder? Actually, no, because this is something that we have learned in. So if based on the order of chapters, this is coming after the functions. So that's kind of obvious for us. If X and Y in mod M has the same remainder, Y and X has the same remainder in mod M. So this is kind of obvious for us, so it's fine if you don't write it, but that's just what's happening behind of that concept, okay? The proof in orange, it's okay if you skip it, but that's just really to make it clear what's happening when you're dividing by M, okay? You're having 1K, which the difference is K times M. I need room to write the transitive. I'm going to move on. Is that fine? Can I move on to this one? Can I go this side? Fine. So one more time. Your transitive. Transitive for this relation. X is related to the Y in mod M, and Y is related to the Z in mod M. Transitive says X is related to the Z in mod M. So this is the same according to what's given to us. M divides Y minus X. This is the same. M divides Z minus Y. And the goal, or what we just call conclusion, or what you want to show is, what was it? Z minus X, M divides Z minus X. So I write the equivalence relation for this one. This is the same as Y minus X is multiple of the M for some K. And then this is the same as, I have to call it K sub 1. Z minus Y is multiple of some M for some K sub 2. And then the goal is z minus x. The goal is z minus x. Z minus x. So add both sides. So this is equation number 1. This is equation number 2. You're adding both sides. So you have y minus x. Here, z minus y here. Here you have mk1, and then here you have mk2. So you factor one m out, and then one of the y's cancel out. So you have z minus x. So this is exactly what I'm looking for. M divides z minus x for some k. Which is the same as saying x and z in mod m are equivalent or congruent. That's a transitive. That's a proof for transitive. Agree with this one? Question? Then the next part of the question, what are the class of equivalency? What are the class of equivalency? I can just write it down over here. What is the class of equivalency? Because we have done 2, we have done 6, we know what is it, right? So what's the class of equivalency for 0? Is going to be the set of all elements, all integers that has the same remainder as 0 in mod m. Class of 1, set of all integers, which has the same remainder as 1 in mod m. So this is for sure 0 is first one, m, 2m, is that true? 3m. Okay, 1, m plus 1, 2m plus 1, forever. Class of 2. Okay, so then, oh, sorry, 2. You can have all the way to the m minus 1. So class of all integers when have the same remainder as m minus 1 when you divide it by m. I'm not going to write 2 because that would be really complicated if you want to write in this one. You have to replace any m by m minus 1. So then it's going to be 2m minus 1. Don't worry about that, okay? So what is it? The question asked me, how many class of equivalency do I have? Yes, and many of those. Fine. That was fine because that was very similar to my actually previous 2 examples of mod 2 and mod 6. This is more interesting. The next example is more interesting because it's a weird relation. It's not a usual relation. Okay, so this is more interesting to work on. Can you think about what's going on? Your relation is from the all integers to non-zero integers. And this is defined for two of them. So means one ordered pay AB is related one and another ordered pay of C and D. So then you're having A times D equals B times C. This is a definition of your relation. And then checking the equivalency relation, reflexive, symmetric, transitive. And then will it be still equivalence relation if you extend this one to the second one, not sorry, including zero. The second one including zero.
It's an alternate name for the Cartesian product and cross product. Is it the same thing?
Is the Cartesian product the same as cross product? No. Cross product gives you a vector, right? So whenever you do the cross product, you end up with a vector. When Cartesian product is the set of ordered pairs. Cross product to be you're talking about calculus 3, right?
Or linear algebra?
Or linear algebra. When you're dividing the cross product, your elements or whichever are just crossing, cross product has to be two vectors. But we are doing the Cartesian product, we are multiplying two sets, not vectors. Okay. So what would be reflexive? Okay, this is more challenging, a little bit more challenging. What should I talk about the reflexive? Reflexive means something is related to itself. Outer elements, inner elements, huh? That's how the product is defined. So your relation is outer elements and your inner elements, which makes sense. Do you agree with this one? Yes?
I don't understand what it means.
What the relation means? Or hear me?
What you just wrote? I'm not following that at all.
You see, so first of all, the relation is not on our hand, that's given to us. So the relation is given to us like this. It's saying you're having something is related to the other one, some element is related to the other element by this definition. What's the definition? Your A times D must be the same as B times C. Must be the same as B times C. So that's not on my hand, it's given in the problem. For reflexive, I'm trying the same thing. Okay? So reflexive says whichever element you choose has to be related to itself.
Okay.
So what's this relation? It says outer elements, A times B has to be the same as inner elements, which is B times A, which is true. Does it make sense? And symmetric. If your A and B is related to the C and D, you have to show C and D is also related to the A and B. So the first one related if A times D equal B times C. The second one is related if C times B equal A times D. If you have this one, you can conclude this one because they are the same. That works, right? They are exactly the same. You know, P, you want to show the Q, but they are equal. They are the same. One more time. What was it? Transitive. Transitive means if you have AB related to the C and D, and you're having C and D related to the E and F. You're supposed to show A and B is related to the E and F, right? So the way that was just earlier was just something called A, something called B, and then something called B, something called C, and then something called A, and something called B. So that was the earlier one. But since here your elements, your domain are Cartesian products, so it's coming with the ordered pairs. Does it make sense? Are you okay with this one? Yes? This one is related because A times D has to be the same as B times C. This time, this one is related because the outers is C and F has to be the same as the inners, which is D and E. And then what I like to show, what I need to show is A and F, B and E. So you have this P, or what we call given or assumption. This is what you need to show. Conclusion. Can I get? So if you multiply both sides of 1 and 2, your A, D, C, F, you have B, C, D, E. If you're looking over here, you need B and C, you need B and E, sorry, but you don't need the C and D. You need A and F, you need A and F, but you don't need the C and D. So you have to divide both sides by, divide both sides by C and D. C and D is non-zero. And that's what you want. That's exactly what you want, which is A and B is related to the E and F. And that's a transitive one.
This is a CD not equal to 0, right? That looks like 7, 0.
Because if C and D are 0, you can't divide them, right? So that then I can answer really this question, right? So would it possible still to make the equivalency relation if your Z star, which not included 0, changing to the Z, which is including 0? The answer is no. Because your second elements of C and D, because the second element of the C and D is not 0 required for the transitive proof. If you're having any possibilities of getting C and D or second element to be 0, you can't. You can't divide it by 0. You're doing something undefined. So the answer is no.
I'm still a bit confused on why CD can't be 0. I thought the way we defined the original set with the Cartesian product of the integers times integers that are not 0 only means the second part of each ordered pair can't be 0. And both times C shows up in the first part. So can't C be 0 make C be 0?
We have to make sure it's what's going on, right? See, your
So is Z without the star AB, and is Z with the star CD? Am I reading that right? I'm not super familiar with the star
I
notation.
thought it was each order pair one comes from, the first one comes from Z without the star, second one comes from Z with the star.
Mhm. So let's just check. So what is the, oh, we are here, okay? Your B is not 0 because it's coming from the star. Your D is not 0 because it's coming from the star. D is not 0 because it's coming from the star. The F is not 0 because it's coming from the star. What
The
are,
C can still be 0?
Yeah, so then can CD 0 making CD 0 sometimes.
so then we have to change this, the first one also to this star. So let's just check one. I'm checking whether the product I've done any mistake. So AD, and CF. This is B, C, D, E, A, B, C, D, E. So this is D and C, this is D and C, so it's required C. So then that's true. Basically, we need to make this one also a star. So change this one, okay? So if this is not a star, that everything is impossible to do. Even this whole thing has to be without the 0. That is true. Your first element, which is the C, can't be also 0, otherwise you can divide it. That was a good point. There should be a typo here. Okay. Oh my God, it's 5.
So can you repeat the conclusion with the Z star statement? Just so I understand.
Your elements, your which conclusion? Conclusion, the whole process was showing something is equivalency relation.
So you said add the star, and then that means what?
Yeah, because according to what you found over here, you're required to divide by a C, and then your C right over here and right over here is coming from the first element. So that's also not to be 0. So that's also another requirement in order to divide it by C. So that's why I just have a typo over here. So C also can't be 0. D can't be 0 too.
So is the conclusion that it is not transitive because with the typo? If Z does not have a star, then it cannot be transitive because under certain conditions it will be 0. Is that what we're saying?
If I keep, you mean this way?
Yeah, if you keep it that way, it's
That's not the
transitive?
transitive. No,
Okay.
that's not
Thank you.
transitive.
Yeah, that's what
No,
but
that's not.
if it is star, then it is.
If you put the star, it's transitive.
Okay.
Okay. I have a little bit time to cover what we skipped in last class. And then I have to show you where is that extra credit that you're supposed to practice this fact. So this is the assignment. And I'm not sure how it shows in your side. That wasn't yours, huh? That was on the problem. Can I go here? I think it's right over here. Yes, exactly. Okay, it's right over here. So what I'm trying to show you right now is exactly part of your work. So if you go on your relation worksheet, some of this one, I can say half of these cases that you're supposed to show is already in your lecture note. Not all of them, okay? But that gives you the idea. That gives you the idea, okay? So if you remember last time I skipped this part, and this is just really trying some of them, so not all of them. So that's in purpose. You can try the rest of them. What was it? Like right over here, we tried to say, okay, if your R as a relation is a set, S as a relation is a set, so what's happened if you do union? What happened if you do intersection? What happened if you do composition, okay? So there are 3 relations that we want to just really see whichever of the properties of reflexive, symmetric, anti-symmetric, transitive transfer after union, after intersection, after your compositions, okay? What you see over here is the properties of the transitive. It says, let's say your first relation R is the transitive relation. Your second relation S also is a transitive relation. So can we figure out, can we check whether if you do the union still keeps the transitive relationship? How about if you do intersection? Does it keep the transitive? How about if you compose them? Does it keep the transitive? Okay. So if I go back to the worksheet, your worksheet has all of them. It says, let's say you have reflexive. Does it keep it after union, intersection, composition? Let's say you have symmetric. Does it keep it after union, intersection, composition? If it's anti-symmetric, and transitive is actually what is in your lecture note. Okay, transitive, I can say it's maybe a little bit, I mean, the most complicated case is the one that you have it in lecture note, because the transitive always is longer to prove. So according to what I have over here, the claim is if you're having union, no more transitive. Union doesn't keep the transitive, intersection does keep the transitive, and then what was it? Composition does not keep the transitive. Okay, that's what is proving over here. Okay.
Is this, the composition, is that from the book? Because it's like a big zero. I'm used to it being very small. I don't know if you copied and pasted or if you wrote that. Did you write this? Or is this from a different textbook?
This is this.
Notation is different.
Yeah, that's different textbook, but it's a
Okay.
composition. You know, even it seems like a zero, right? Not even
Yeah.
like a O. It has to be small O.
It might be the wrong font or something.
Hmm.
Yeah, because it looks different. Yeah.
Okay, are we ready? Do you know what we want to do right now, right? So what was the question asked us? R is a transitive, S is a transitive. I want to do a union and say that's not the transitive anymore. Okay, I want to do union and says it's not the transitive anymore. So we can go with the counter example. We can just disprove it. So it's both of them are possible. Okay. So again, I wrote the steps for you because I assigned for you similar problem to practice. Okay. So for your worksheet. So let's say you want to prove something is transitive. What do you need to show? In order to show something is transitive, you have to show if X and Y is related, Y and Z is related, so then X and Z is related. So related in this time is going to be inside the union. X and Y is related, Y and Z is related means they are in the union of these two relations. So then your goal is to show whether X, Z is related or not. Okay, so whether X and Z is related or not. Does it make sense? First of all, let's say if you're having these two inside the union, if you're having something inside the union, either is in the R or in the S. Does it make sense? If it's in the union, it could be either in the R, either in the S. Okay? No? What does it mean if you have two elements in the union?
Either or.
Yeah, it could be either in the R, it could be either in the S, it could be one of them in the R, one of them in the S. That's possible, right? If both of them is in the R, since R is transitive, I won't have any problem with that. Because if both of them is in the R is transitive, since R itself is transitive, that's easy to conclude X and Z is part of the R. So then it's inside the union also. So that's perfect. We don't have any problem with this case. If both of them also is in the S, also we have the same case. In the S, transitive S gives you XZ in the S and then is the union, okay? So if both of them is staying in the same R or the same S, you won't have any problem because R and S are transitive. Your question or the place that it fails to be transitive is if one of them to be in the R, the other one to be in the S. If one of them is in the R, the other one in the S, there is no guarantee to say, there is no, even though when you have R and S transitive, there is no guarantee to say XZ also going to be in the R or S, but then it's in the union, okay? So then I have some example for disproving. Let's say 1, 2 is one of the elements that's sitting in the R, 2 and 3 is another element that's sitting in the S. Okay. So what I need is 1 and 3 in the union. What I need 1 and 3 in the union. So I define my R to be exactly same, only one unique element of 1 and 2. And then I define the S to be exactly including 2 and 3. And then your union is going to be 1, 2, 2, 3, which does not have 1 and 3. So that fails to be transitive. So I simply make my R and S to have only one element. One single element by itself is transitive. And then one from R, the other one from S, put them together. There is no third one, which is 1 and 3 to make it transitive. So that fails. Okay. Again, this is really good hint for your rest of reflexive, symmetric, anti-symmetric. That's why I wrote it in the steps. And for the intersection, we don't have any problem. For intersection, it makes really sense, okay? So if you're having anything in the intersection, it's sitting in both of R and it's sitting for both of the S. So that means because R and S are transitive, so for sure, intersection is going to be transitive. It's really easy. Because it's sitting into both when you're doing in intersection, okay? Oh, sorry, I have to stop. I have to stop. So you can just check the intersection, sorry, the composition too. We have nothing left for the relations, okay? So we have nothing left for the relations. I think you're good to do the homework this time.